Hey guys, derivatives of inverse functions is today's lesson. The last lesson was derivatives about some specific inverse functions, inverse trig derivatives. Now we're going to be talking about derivatives of inverse functions in general. So before we do that, we're going to have to kind of remind ourselves about some properties of inverse functions. And we're going to get started with that right now, actually. So one of the things we need to review is how the graphs of inverse functions are related to the original function. So here I've got some function, looks like some x cubed function right here. And we are going to show what the graph of the what the graph of the inverse function does. You might recall that inverse functions undo each other. They're opposites in a way to speak. And they have a lot of uses. Anyway, for the inverse though, here's a graph of the inverse function. I'm also going to show you the line y equals x. So you might recall from pre-calc that when you have a function and its inverse functions are always reflections over the line y equals x. All right, when plotting the inverse, where do these points translate to? So this point here is a point 2, 4. When it is translated over that y equals x, it lands right here, which is a point 4, 2. That point there, 1, 2, it ends up landing right here, which is a point 2, 1. This point 0, 1 lands right there at the point 1, 0. You might be noticing a pattern. Same numbers, but the order is switched. That shouldn't come as much of a surprise for us. This is an x value, that's a y value. It ends up being the x and the y switches. That might sound familiar to you. That's one of the ways we found out what an inverse function was. We literally switched the x and the y's, and then we solved. So that's one of the properties of inverse functions, that has the x and the y values switched. All this should be old news, but it's probably good to have it refreshed and come back to us. All right, so recall, inverses have the x and the y values switched. We're actually going to remember how to find our inverse functions here. So that's what I'm going to do next. I'm going to have to use my iPad though, so I'm going to switch screens in 1 minute. All right, so if f of x is equal to x cubed and I wanted to find f inverse of x, don't forget that little symbol there that looks like an exponent. It's not an exponent. Where there's a -1 there, it means the inverse function. Inverse functions, again, undo each other. So the way we learned to do this in algebra was we would rewrite this equation as y equals x cubed. Same exact equation, I just put a y in there. And then we switched the x and the y. So instead of y equaling x cubed, we would write x equals y cubed, which is a weird thing to do. But as soon as I did that, I now have my inverse function. This is my inverse function. It's just not written in a nice way. To write it in a nice way, I normally want a y equals equation. So I got to get rid of this. I got to get rid of that exponent. How do I get rid of an exponent of 3? Well, I take both sides to the 1/3 power. The reason we do that and the reason it works is, again, inverse functions undo each other. So when I switch that x and the y and then I solve for y, I'm literally undoing everything that had happened to the original one. Like in the original, you take some number and you cube it. So now I'm going to undo that. I'm going to take it to the 1/3 power, which is the opposite of cubing something. So I end up getting y is equal to x to the 1/3. That is my inverse function, which then I can write in that notation. F inverse of x is equal to x to the 1/3 power. That is the function that would undo this function, right? It's the opposite. For that first function, I'm cubing it. For my inverse function, I'm taking it to the 1/3 power. They undo each other. All right. In this section, we're going to explore some relationships between an original function and its inverse. So here I've got f of x equals x to the 3rd, and I've got its inverse function, f inverse of x equals x to the 1/3, which we had just found out earlier. We're going to plug in a few values, find a few things, and then we're going to notice something about them. So first off, f of 2. f of 2 is just plugging a 2 into the function f. So plug a 2 into there, I'd have 2 to the third, which is just 8. F inverse of 8 is just plugging an 8 into the inverse function. That would be 8 to the 1/3, which is 2. Now, there's a few things we need to talk about. First off, I shouldn't be surprised about that line. Notice here, when I put a 2 in the original, I got an 8 out. When I put an 8 into the inverse, I got a 2 out. Those are the same numbers, but switched. That shouldn't surprise us because inverse functions undo each other. When I put that 2 in and I got an 8 out, and then I put an 8 into the inverse function, it undid everything that happened, and I ended up right back at 2. Remember, with inverse functions, the x and the y values would be switched. So if the original function has the point 2, 8 on it, which it clearly does, when I put a 2 in, I get an 8 out. The inverse function should have the opposite point in there. It should have the point 8, 2. Right? So that shouldn't come as a surprise. The second thing we should talk about is this 8 to the 1/3. We should know how to find that without a calculator. You'll notice I just said it was 2, and I didn't flinch about it or anything. If you're not sure about how to find the answer to a fractional exponent like that without a calculator, we should talk about that. So I'm going to talk about that now. If you already know that and you can find 8 to the 1/3 or like 8 to the 2/3, go ahead, fast forward through this part. Otherwise, you might want to watch this. All right, so I'm just going to do it off to the side here. If I have something like 8 to the 1/3, that is another way of writing a radical. Radicals with that square root sign. In this case, instead of a square root, it'd be the third root. So 8 to the 1/3 is the same exact thing as finding the cube root of 8. No difference. Cube root of 8 is just finding some number that times itself 3 times is 8, right? So if it's 8 to the 1/3, I need to find something that times itself 3 times it's 8. Same as cube root of 8, no difference. Some number that times itself 3 times 8 times itself 3 times is 8 is 2, because 2 times 2 is 4 times another 2, that's 8. This is equal to 2. If I had a problem like 8 to the 2/3, that shouldn't be a problem because that's the exact same thing as 8 to the 1/3 all squared, because of my my properties of exponents. If I have something like this, 2 times 1/3 is 2/3, that's the shortcut. Those are equivalent. Well, 8 to the 1/3 is something we can find out. We just did here. It was 2. So 8 to the 2/3 would be 2 all squared because of that square there, which would just be 4. All right, back to the calculus. All right, next we're gonna find the derivative of f at 2. Well, f was x cubed, right? From way up here. Just gonna rewrite it there. F was x cubed, so f prime, the derivative, would be 3x squared. So f prime of 2 would just be plugging a 2 into there. 3 times 2 squared, which is 3 times 4, which is 12. F prime of 2 is equal to 12. Let's do the same thing for the inverse function. F inverse prime of 8. So the derivative of f inverse at 8. Well, f inverse is right here. So its derivative would be 1/3 x to the negative 2/3, right? Because 1/3 minus 1 is negative 2/3. My derivative then, evaluated at 8, would just be plugging an 8 in. 1/3 8 to the negative 2/3. We could plug that into a calculator, but I actually want my answer as a fraction for this. And yes, a calculator can also give you the answer as a fraction, but this is also one that you should be able to do by hand and could show up on an AP exam where you're expected to do it by hand. So let's make sure we know how to do that. that would be, let's see, if I did this by hand, I would probably rewrite that as 1 over 3 times 8 to the 2/3, right? Because a negative x component can be rewritten in the denominator. 8 to the 2/3, we had talked about this just briefly with fractional exponents. That's 4. So this is a 1 over 3 times 4, which is 1/12. All right. Here's the big thing I wanted to get to. When I had here, from here, I saw that I had the point 2, 8. And then my inverse function had the point 8, 2, which we said again was no surprise. But here's the bit of the surprise. My derivative at 2 was 12. The derivative of the inverse function at 8 was 1/12. That's no accident or that's not just by circumstance. It actually always happens. Turns out that the derivative of my inverse function at that point where it switched is the reciprocal slope. And if this one has a slope of 12, that one will have a slope of 1/12. We're going to talk about that a little bit more and kind of try to cement that knowledge down. All right, so here's the big thing that we just discovered. It's kind of weird. It's not too bad though. In my original function, I had the point 2, 8. That means on my inverse function, I'm going to have the flipped point, 8, 2. In my original, at that point, I had a slope of 12. If that happens on my inverse function at the correlating point, I'm going to have a slope of 1/12, the slopes being reciprocals to each other. Please note, not opposite reciprocals, that's perpendicular lines. These slopes are not perpendicular slopes. They're just reciprocal slopes. All right. Here's a note about that stuff. It's kind of mathematical. It can help some people. I find just having the idea of this is more beneficial. But if you like it, here's exactly what we talked about in some more math terms. It says given f and its inverse f inverse, right? If f of a equals b and f prime of a equals c, so that's the original function is some point b and the derivative is some slope of c, then f inverse of b equals a. This part is speaking to the fact that the points switch values, right? If I have a comma b on the original, I'll have b comma a on the inverse function. And f inverse prime of b is equal to 1 over c. This is getting to the point of if my slope on the original is some value c, my slope on the inverse for that correlating point would be 1 over c. All right, let's actually do a couple problems. There is a theorem, it says derivatives of inverse functions. It says if f is differentiable on AB and its derivative never equals 0, then the inverse exists and is differentiable on the interval f of a to f of b. We can talk a little bit about this. The reason that, let's talk a little bit about this. All right, so first off, this is just saying f is differentiable, which means you've got some functions you can take the derivative of. And the derivative never equals 0. The reason that part is important for this particular theorem is because it's going to be talking next about the derivative of the inverse. Well, if the derivative equaled 0 on the original, the derivative of the inverse would be the reciprocal of 0, but the reciprocal of 0 would be 1 over 0, and you can't divide by 0, which would mean I would have an inverse slope that doesn't exist. It'd be a vertical slope instead of a horizontal slope, right? So this is just saying, hey, we don't want, if you want the inverse to exist and be differentiable, then the original function can't have a slope of 0 because otherwise the inverse function would have a vertical slope, which is an undefined slope, which means the inverse derivative doesn't exist at that point. Not a huge thing. Again, it's more important that we understand this concept. All right, let's actually come up with a couple of things. This theorem means it's possible to find the value of the derivative of inverse without actually having to define the inverse function. The AP Calc test does ask questions about this derivative of the inverse thing, and it does it in such a way that you really need to know this. Now, I will tell you right now that it is fairly low importance. I mean, it'll only have like 1 or 2 questions about this on the AP exam, probably only 1. But if you know it, it's not hard and it's a free point. So as far as importance, there are much, much more important things like the chain rule and implicit differentiation and the product rule. Like those are hugely important. This is a minor importance, but it's some free points on the AP exam if you have it. So definitely spend some time on it. All right, finally, let's actually do some problems. So here's one example problem, just to make sure we understand it. I'm going to find f of 1 and then f prime of 1. Well, f of 1 is just easy. You plug a 1 into my function f. So if I plug a 1 into there, I'll have 1 cubed plus 2 times 1 plus 1, which will be 4. F prime of 1, I need to plug 1 into the derivative. So f prime of x would be 3x squared plus 2. So plugging a 1 into that would be 3 times 1 squared plus 2, which is 5. Now, if I ask questions about the inverse function, yes, I could try to find the inverse of this thing, f inverse of x, by switching the x and the y and doing all of that work. But when I know this calculus knowledge, I actually don't need to do that, because right here on the left, when I plugged in 1, I got a 4 out. That means on my original function, I had the point 1, 4. So it should come as no surprise that my inverse function is going to have the point 4, 1. In other words, when I plug a 4 in, I should get a 1 out, right? These points correlate to each other. So the derivatives, or the slopes of those points, are going to be inverses to each other. My slope on the original function was 5. So my slope on the inverse function is going to be 1/5. I didn't have to find f inverse. I could find those values without it. All right, here's an example AP problem. This is how they'll throw it to you. We're going to talk about ways to solve it. If you want to try it on your own, go for it. Just pause the video and do it. Otherwise, I'm going to work through it with you. All right, the example AP problem says, let f be a differentiable function such that f of 3 is equal to 15, f of 6 is equal to 3, f prime, let's do that in a different color. F prime of 3 is equal to -8, and f prime of 6 is equal to -2. The function g is differentiable, and g is equal to the inverse of f. So g is equal to f inverse of x for all x. What is the value of g prime of 3? Okay, they threw a lot of information at you. The key to getting these problems right is understanding what that information is. A lot of the times, it's a lot easier to solve these problems by actually doing a quick sketch of the graph. So I don't really know what f looks like, but I know it's got the point 3, 15 on it. So there's the point 3, 15. I also know that it's got the point 6, 3 on there. Because when I plug a 6 in, I get a 3 out. That's really all I know about it. Well, not really, because I also know the slopes. I know the slope at 3 is -8. So I'm going to do a different color here. So the slope at that point is equal to -8, right? It's got a pretty steep downward slope. And I know the derivative of 6 is -2, so I know the slope at that point is -2. All right, Now I think we're ready to answer this question. This one is asking for g prime of 3, right? Well, on the original, I've got 2 points. Original, inverse. On the original, I've got the point 3 comma 15, and I've got the point 6 comma 3. That means on my inverse, I know of 2 points, 15 comma 3, right? The x and y switched, and 3 comma 6. Now, this is asking about g prime, let's see if I can have it, g prime of 3. So it's asking about the slope right there, right? The derivative of my slope. This is my g function. I'm asking what is the derivative at that point, at the point x equal to 3, right? Well, on my original, that would be correlate to the point 6 comma 3. That one had a slope of -2. So this point, g prime of 3, is going to have a slope -1/2, -1/2. So they gave us more information than I needed. I didn't need to know this point at all. But they did that because a lot of times the fact that there's a 3 there and there's a 3 there, it throws people off. So it can be nice to correlate them with the points that they would correlate to on the inverse. 3 comma 15 would correlate to the point 15 comma 3. I'm not asking for the slope at the point at x equals 15. I'm asking for the slope at x equal to 3. All right. It can be weird, but there's only a few problems, 28 through 31. Give them a try. As always, feel free to stop by my office hour. I can help explain this more. I'll see you guys later.